We have been discussing the application of Monte Carlo simulation procedures for simulating response of randomly excited dynamical system. So, we will continue with this discussion. So, the basic framework of our solution strategy is displayed here. This is the dynamical system which is excited by random excitation. So, there is an ensemble of excitations and a complete description of f of t is assumed to be available, and based on that, using methods that we have already discussed, we can generate an ensemble of time histories, samples of f of t, which are compatible with the given probabilistic description of f of t. Then for each sample of this excitation, we will use deterministic solution procedures and produce a corresponding response time history. So, associated with each sample of input, there will be a sample of output, and we get an ensemble of response time histories, and this ensemble of response time histories now need to be processed using methods of statistics to arrive at a probabilistic description of x of t. We will estimate, for example, mean of the response, covariance of the response, power spectral density, probability distributions, density functions, first passage time, extreme values, so on and so forth, using suitable estimators. So, this is the framework. We have now described how to simulate samples of f of t compatible with the given description of joint density of f of t, and we have already discussed how to calculate the dynamic response of a system given the sample of an excitation, that is a deterministic analysis of response that we have discussed, and we have also discussed how to characterize estimates of different properties of x of t, and what are the properties of these estimators and sampling distributions and things like that we have discussed. Now, let us proceed. First, at the outset, we will ask when does the Monte Carlo simulation procedure becomes useful. Let us start by considering linear time invariant systems under Gaussian excitations. So, this is the Gaussian equation mx double dot plus cx dot plus kx equal to f of t, which specified initial displacement and velocity vector. X is a vector, this represents a multi-degree freedom system. F of t is a Gaussian random process, it can have a non-zero mean, it can be non-stationary. Now, if we are interested in characterizing the response in terms of its moments, like for example, mean, covariance, etc., or PSD matrix of the response, if a steady state solution is possible, that is when f of t is stationary and we look at steady state response, we have an exact solution for this PSD. Similarly, if we are interested in joint probability density function of response vector at different time histories, we know that the system is linear and excitation is Gaussian, therefore, the joint probability density function is also going to be Gaussian. So, if we are interested in only these quantities, moments or power spectral density or joint probability density functions, actually there is no need to use Monte Carlo simulations to solve this problem. Actually, it is a wasteful approach compared to the elegance of an exact solution. It does not offer any advantage if our interest is limited to only this kind of response quantities. On the other hand, if we are interested in say level crossing statistics or first passage times or distribution of peaks or extreme value distribution, even for linear time invariant systems under Gaussian excitations, we do not have an exact solution to probabilistic description of these quantities. We have used certain heuristic arguments and postulated models. For example, we assume that if levels are high, we can model the number of times a level is crossed using Poisson models, and first passage times become exponential, and peaks are Rayleigh distributed for narrowband processes, and so on and so forth. Similarly, extreme value distribution, we arrived at a Gumbel model for the extreme value of the response. But all the solutions that we developed are essentially approximate in nature, and they are not robust in terms of variations in say the excitation characteristics or damping characteristics in the system. So, in such cases, of course, Monte Carlo simulation procedure offers useful means to tackle the problem even for linear time invariant systems. if we encounter more complicated situations, for example, system behavior is nonlinear, or there are parametric excitations, or excitations are non-Gaussian nature, or system parameters are uncertain, therefore, we use random variables or random process models for even to describe the system parameters. In all these cases, the system cannot be analyzed exactly, and invariably one has to go for an approximate analytical solution or the Monte Carlo simulation procedure. Similarly, just to reiterate, if characterization of reliability measures of response like first passage times or extreme value distributions are of interest, the Monte Carlo simulation procedure becomes, it wins over the other methods. This is the broad context in which we are interested in Monte Carlo simulations. Just to get a feel for the kind of problems where we could apply Monte Carlo simulations, we will consider an inhomogeneous Euler-Bernoulli beam which is excited by a force which varies both space and time, and it is also excited by a parametric excitation P of t, and we assume that the flexural rigidity, mass per unit length and damping coefficient are all spatially varying, and also the boundary conditions, we do not have perfect hinge or perfect free end conditions. There are some flexibilities at the joints, and they are captured through spring constants K1, K2, K3, K4. Now, the load f of x of t could be, for example, wind load, and this can be random in nature, it can vary randomly in space and time. The parametric excitation could be random. This psi of x comma t is a quantity that represents modeling error, and this also could be randomly varying in space and time. The quantities ei of x, m of x, c of x vary in space, spatial coordinate x, and they can also be random, and they can be modeled as random field. If their variation with respect to x is not very significant, they can as well be modeled as random variables. So, this is a stochastic boundary value problem, it is a stochastic partial differential equation, and an exact solution to this even to characterize mean of the response is not available, but on the other hand we can simulate samples of f of x comma t, psi of x comma t, ei of x, m of x, c of x, etc., and use deterministic procedures to find out the response of this system for each realization of these stochastic quantities, and we can produce an ensemble of response quantities, and that ensemble can further be processed to get descriptions of interest. Now, we have already covered in this course procedures for simulating samples of random variables and random processes compatible with the given probabilistic description of these quantities. Similarly, we have described the procedures for solving sample problems in dynamic response simulation. That means, if a beam is excited by a dynamic excitation, we have already developed the necessary procedures to produce the response time histories using modal expansion and so on and so forth. Similarly, we also covered the procedures for processing samples of response time histories. So, basically in implementing Monte Carlo simulation procedures, we could ask, where does actually the difficulties arise? Given the coverage of topics in this course, there are two difficulties that still remain. One is treatment of spatially varying randomness. So, I talked about flexural rigidity being function of x, m of mass per unit length being function of x, etc., and these quantities appear as coefficients in the governing differential equations, and these quantities could vary in space, and that this type of problems we have not yet discussed, and one need to generalize the say the finite element method for handling inhomogeneous beams to take into account the additional complexities of spatial variations, spatial random variations in system parameters. That takes us to the topic of stochastic finite element method. On the other hand, there is yet another difficulty that is associated with treatment of calculus associated with systems driven by white noise or filtered white noise excitation. So, what we would do in this lecture is we will cover the second aspect, and we will consider how to numerically simulate samples of response of systems which are driven either by white noise or by filtered white noise, and that would require a preliminary discussion on elements of calculus of Brownian motion processes. So, this is what we are going to do in this lecture. So, the topic for today's lecture is simulation of dynamical systems driven by white noise excitations. So, the governing equation is written in the form dx of t is f of t comma x of t dt g into dB of t with specified initial conditions. dB of t is the increment of Brownian motion process. The range of problems that are represented through this equation is quite wide. The system could be nonlinear, the excitations could be parametric or external, and these excitations could be straightaway white noise processes or they could be filtered white noise excitations. If they are filtered white noise excitations, the state variable associated with these filters get augmented with the system states, and x of t in this case represents an extended vector, and we could deal with any desired measure of response like moments, autocovariance, power spectral density, first passage time, extreme value, so on and so forth. Now, what is the major issue? The major issue here is how to take into account peculiarities of calculus associated with Brownian motion processes. If we quickly recall, we have already seen the issues associated with a random walk becoming a continuous time random process, and we will return to that shortly. Before that, I would like to cite this reference. This is a book by Cloydon and Platon which describes extensively the numerical solution of stochastic differential equations, and the lecture that I am presenting now, this will be a very, for this lecture this will be a very useful reference. So, we will begin by recalling Taylor's series for deterministic functions. Suppose I consider a function f of t which is well behaved, that means it is sufficiently smooth, that is we can differentiate it as many times as we wish. We can consider f of t and write it as f of t star plus t minus t star, and we can expand this function around t star and we write it as f of t star t minus t star into f dot t star plus delta t square by 2 factorial f double dot etcetera etcetera. So, this is the familiar well known Taylor series expansion for f of t. Now, I will take f of t star to the left hand side and denote f of t minus f of t star as delta f of t, and I will call t minus t star as delta t. So, I can rewrite this in terms of this increment, delta f of t is delta t f dot t star plus delta t square by 2 factorial f double dot etcetera etcetera. Now, if we take now the limit of delta t going to 0 and delta f of t going to 0 and use that here, we get the well known result df of t is f dot of t into dt, because delta t square, delta t cube etcetera all of them would go to 0. Now, this would not happen if f of t is a Brownian motion process or a function of a Brownian motion. So, what happens in that case? So, we will quickly recall this, again a recall of what we have already discussed. This is simple random walk. If xi I equal to 1 to infinity is an IID sequence of random variables, and each random variable taking two possible values delta x and minus delta x with probability p and 1 minus p, we can evaluate the mean, that is delta x minus delta x into p minus q, and the mean square value and the variance. So, this we have done. The variance of this two state random variable is 4 p q delta x square. Now, let us assume that there is a time axis and divide the interval 0 to t into n sub intervals, each of which delta t, so that n delta t is t. Now, I define a random process S of t as a sum I equal to 1 to xi. Now, the expected value of S of t we can evaluate, and we can show that it is t into p minus q delta x by delta t. Similarly, variance can be shown to be given by this quantity. Now, this is the simple random walk process. Now, It is a discrete state, discrete parameter random process. Now, I would like to consider the limit of delta x going to 0 as delta t going to 0. This is a typical situation that we envisage in a deterministic sense. So, what happens to the expected value of s? It becomes a quantity delta x by delta t, which is which has acceptable meaning, but variance of s of t goes to 0, and this is not an interesting limit. That means, under this particular limiting operation, s of t becomes a deterministic function since the variance is becoming 0. So, it is not an interesting limit from point of view of probabilistic treatment of random walk. Now, on the other hand, if delta x square goes to 0 as delta t goes to 0, then what happens? The variance of s of t now goes to a quantity which is non-zero, and by minor adjustment of these terms, we can show that mean of s of t becomes mu t and variance becomes sigma square of t, and this is quite an interesting limit. This resulting random process is a Wiener process that we have seen, and for this Wiener process the complexity associated with trajectories is that as delta t goes to 0, delta x square goes to 0. So, this will create certain additional complexities when we have to deal with calculus of these random processes. So, s of t under that specific limiting condition, as we know, is a Wiener process. This is a continuous state and continuous parameter random process. It is a Gaussian random process because there is addition of IID sequence of random variables and we invoke central limit theorem, and that process is Gaussian. Now, the process is non-stationary, you can easily see that because mean is function of time and variance is also a function of time, and if mean is 0, the Wiener process is known as a Brownian motion process. So, we in the further discussion we deal with Brownian motion process. Now, let us try to now consider the Taylor's expansion of B of t. Just as we did for f of t, if we now repeat those steps, if B of t is a Brownian motion process, I can write it as B of t star plus t minus t star, and following the usual steps I can write this step as well and introduce delta of B of t as B of t minus B of t star and delta t as t minus t star. Now, I can again write this step as well, which is quite similar to what we did earlier. Now, we have to now use this limit delta B of t goes to 0 as square root delta t goes to 0. It is not that as delta t goes to 0, delta B of t goes to 0. So, consequently what happens, dB of t will now be no longer just this term B dot of t dt as was the case for f of t, but now we get a new term delta t square by 2 factorial B double dot of t. This additional term introduces various complexities when it comes to numerical solution of the governing differential equation. Now, I will state some rules and I will prove it in due course, but to begin with we can follow these rules, accept these rules and see what will be the consequence, and then we will see how it can be shown. The rules is square of dB of t is dt, dB of t dt is 0 and dt square is 0. So, what does that mean? Let us consider a stochastic differential equation which is scalar dx of t a of t dt plus b of t dB of t and x of 0 is x naught. Now, if I square dx of t whole square, I get a dt plus b dbt whole square. This is a square dt square plus b square dB t whole square plus 2 ab dbt. Now, we follow the rules, dt square is 0, dB of t whole square is dt and dbt into dt is 0. So, I get b square of t into dt. Now, let us consider a function u of x of t. What is du? Du is u prime into x dot, which is this, plus half of u double prime into x dot square, because that is what I have to see, this is what we have shown here. So, this is a similar logic is being used here. So, if I now substitute for x dot in terms of x dot is a dt plus b dbt and then carry out this operations and use those 3 rules, I get du as u prime a of t plus half u double prime b square of t dt plus u prime b of t into db of t. So, this is known as Ito's formula. Now, what happens to dx of t whole cube? Just to make sure that this is 0 as we have been telling, we can quickly do this calculation dx of t into dx of t whole square, and dx of t this is b square of t dt. Just now I have shown dx of t whole square is b square of t dt, and this is 0. Now, as an example, let us consider u of t is b square of t. If I now follow these rules, Ito's formula, I get du as u prime db of t plus half u double prime db of t whole square, and now if I use the fact that u is b square, I get now this as 2b of t into db of t plus dt. So, this is a new correction because of peculiarities of paths of b of t. Similarly, if we consider now u of t to be exponential of b of t, what will be du? U prime db of t plus half u double prime db of t whole square. Now, u prime is exponential bt dbt plus half exponential b of t into dt. So, this again is a new term. Similarly, we can use rules of this calculus. Now, if u of x is ln x, according to the stochastic calculus, du will not be simply dx by x, but there is an additional term that will be, if you include that, it will be dx of x plus half of dx by x whole square. Similarly, what is the product rule? D of xy is dou by dou x of xy dx plus dou by dou y of xy dy plus these additional terms which we have to include now. And if I include this and use the rules that we have been talking about, we get, in addition to the traditional y dx plus x dy, there is a new term which is dx dy. This has to be borne in mind. Now, I stated those 3 rules, we can quickly see if we can offer a simple proof for those things. Suppose I consider how to prove that db of t whole square is dt. Now, what I will do is, I will consider the time interval 0 to t and divide it into n intervals of which delta t such that n delta t is t. We will fix t, and now let us define 0 to t db of t whole square as this summation limit delta t going to 0 I equal to 1 to n, dbt is increment of Brownian motion process. So, I will write it as b of t I minus b of t I minus 1 whole square. Now, I will define E I as b of t I minus b of t I minus 1, and I will rewrite this sum as limit of n tending to infinity E1 square plus E2 square plus so on and so forth En square. Now, I will rearrange the terms, I will multiply and divide by t, and in the denominator I will write for t n delta t, and I will rewrite this summation in this form. This is the form. Now, we will fix t to n delta t and allow now n to infinity and delta t to going to 0. Now, we know that E1 is a Gaussian random variable, E1, E2, E3 they are all Gaussian, and this term inside the brace represents sum of squares of Gaussian random variables, and we know that it is a chi-square random variable, and we can verify that parameter for that is 1. And if I now use law of large numbers, we can show that this limit is actually E1 square plus E2 square plus so on and so on, En square is actually t. So, consequently, I get 0 to t db of t whole square is t. But we know that 0 to t ds is equal to t. So, if you compare this with this, we can now infer db of t whole square is dt. Now, how do you show that dt square is 0? This is straightforward. You follow the same logic, write 0 to t dt square as limit delta t going to 0 I equal to 1 to n delta t square, and if this becomes n delta t whole square delta t going to 0, and this can be written as limit of delta t going to 0 n delta t into delta t, n delta t is t and the other delta t goes to 0, therefore, answer is 0. So, you can similarly show that db of t into dt is 0, this I leave it as an exercise. So, we have now a glimpse of the consequence of delta x square going to 0 is delta t goes to 0 in a simple random walk leading to the Brownian motion process. So, that has to be borne in mind whenever we deal with Brownian motions. Now, our objective in discussing this is to develop numerical schemes for solving stochastic differential equations. So, if we now go back to deterministic differential equations, we know that the schemes for integrating these ordinary differential equations, deterministic ordinary differential equations essentially are developed using Taylor series expansions. We represent that, we use the Taylor series expansion and truncate it at a certain order, and that leads to various types of integration schemes. So, this we need to now extend that logic to deal with stochastic differential equation. So, to facilitate that, we will quickly recall Taylor series, but in a slightly different form known as integral version of Taylor series. Now, let x of t be a scalar deterministic function. Now, consider the differential equation dx by dt is a of x of t, and the condition on x of t is given at t naught to be x naught, and t naught itself can take values from 0 to capital T. This can also be written as x of t as x naught, which is at t equal to t naught, and then integral of t naught to t a x of s ds, because dx is a x of t into dt. So, if I integrate that, this is the derivative and this is the time length. So, it should give the change in x of t over from t naught to t. Now, we will assume for purpose of discussion that dA of x of t is well behaved, that means it is sufficiently smooth, which means that you can differentiate it as many times as you wish. Now, we will begin by considering the function f of x of t. d by dt of f of x of t is dou by dou x of f into dx by dt, that is dou by dou x into f. For dx by dt I will write now a of x of t. So, I will call this as L into f, where L is the operator a into dou by dou x. So, therefore, f of x of t can be now written as f of x naught plus t naught to t Lf into ds. Fine. Now, if f of x of t is x of t, we should recover what we have already seen. Lf will be a, Lf will be a, and we recover from this equation, that is from this equation we recover what is already derived by an alternate argument. Now, what we will do now is, for this integrand we will now write a Taylor's expansion, I mean this expansion. So, if I take now in this formula f to be a of x of t, I will get a of x of s to be a of x naught plus t naught to s L a dz. Now, this I will substitute into this formula, and I will get x of t is x naught, that is this x naught, plus t naught to t, that is this. For a of x of s here, I will write this expansion. So, I get a of x naught plus t naught to s L a x of z dz ds. Now, I can rearrange these terms and write it as x of t is x naught plus a of x naught t naught to t ds plus this double integral. I can proceed further and now consider f to be La, and again use this formula and represent La as La x of z as La x naught plus t naught to z L square a du. So, this I can substitute in x of t, and if I repeatedly do that, I will get now at this stage x of t is x naught plus a x naught t naught to t ds plus this triple integral, and that can be simplified, and I can write it as x naught plus a x naught t naught to t ds plus L a x naught into this double integral t naught to t naught to s dz ds plus a remainder term R3, which is this integral. Of course, now I can proceed further by taking L square a to be f, and again use this kind of representation for L square a and go on substituting into this. So, that finally leads to the so called Taylor series expansion in its integral form, which is f of x of t given by this. This will be the starting point for developing numerical schemes for solving differential equations, and the question that we need to ask now is, how do we generalize this when x of t is a filtered white noise or a white noise process itself, or when x of t is governed by this stochastic differential equation. So, the question therefore, we need to ask is what is the generalization of Taylor series when x of t is governed by this SDE. So, how do we proceed? So, this we will again rewrite this SDE, that is dx of t is ax of t plus b dbt and initial condition at t naught, and consider f of x of t is f of x t naught plus t minus t naught, and now I will write the expansion for this bearing in mind the ITOS formula. So, this will be f of x of t naught plus t naught to t plus this term inside the brace is not just the first term as shown here, but there is a second term into ds plus this additional term that we get b of x of s dou by dou x f x db. This is this follows from the ITOS formula. Now, I will introduce two operators L naught and L1. L naught is a dou by dou x plus half b square dou square by dou x square, and L1 is b dou by dou x, and with this notations L naught and L1 I can write f of x t in the form of f of x of t naught plus this integral L naught f ds plus L1 f dbs. Fine. Now, if f of x of t is now x of t, I need to recover what I know very well is the answer. So, x of t is x of t naught plus t naught to t L naught x plus t naught to t L1 x dbs. Now, I know I can operate now L naught on x and L1 on x. If I do that, I get x of t is x of t naught plus t naught to t a ds plus t naught to t b dbs, which is nothing but equivalent of this SD. This is actually the stochastic integral that we are interested in. Now, let us begin by considering x of t in this form, x of t naught plus integral a ds plus integral b dbs, and we will now apply ITOS formula on a and b, a of x of s and b of x of s, which are in the integrands of these two integrals. If I do that, I will get now x of t to be x of t naught to t, and for a of x of s I get this terms inside the brace as the application of ITOS formula on this leads to this term. Similarly, the application of ITOS formula on b leads to this second term. Now, I can proceed further. I am basically following what I did for deterministic Taylor's expansion with additional care, additional steps to take care of the peculiarities of Brownian motion process. So, x of t can be written as x of t naught a into t naught ds plus b into t naught dbs plus this remainder term, which has L naught a dz ds plus double integral L1 a dbz ds plus L naught b dz db plus L1 b dbz dbs. Now, we can now continue to apply the ITOS formula on the integrands in the remainder term. For example, if we now consider L1 b x of z and apply ITOS formula on that, I can get for this a term like this plus a remainder which will absorb these terms plus the remainder from representing this, the terms other than these which are already included here. That R bar in fact you can derive you can show that it consists of double integrals and triple integrals of this kind. Of course, on this L1, L1b I can again apply the ITOS formula and go on doing this, and a more general representation for ITO-Taylor's expansion can thus be found. But what is important to note here is, if we now focus attention on the expansion at the second term level, I have x of t naught plus a into t naught t ds plus b into T naught t dbs plus L1b into a double integral T naught t T naught to s dbz dbu. Now, the right hand side has these integrals T naught to t ds, T naught to t dbs and this double integral T naught to t T naught to s dbz dbu. These are all random variables. The first term of course is not random variable, but these two are random variables. These are called multiple stochastic integrals. The inclusion of higher order terms of course leads to more general forms of MSI. MSI is multiple stochastic integrals. So, Ito-Taylor's expansion, thus on the right hand side we will go on getting these MSIs which are random variables. Now, we can make a few remarks at this stage. This Taylor series plays the central role in developing numerical integration schemes for ODEs. This is true for deterministic set of ODEs anyway. Schemes with different orders can be derived by truncating the series at different levels. This is true for deterministic ordinary differential equations. The numerical simulation of solutions of stochastic differential equations is based on the application of the truncated Ito-Taylor expansion. Just as in deterministic case we are using Taylor's expansion, truncated Taylor's expansion, here we have to use the truncated Ito-Taylor expansion. Now, I will state the problem and I will provide the recipe for the numerical scheme to integrate. I will refer you to the book by Cloden and Platon which contains all the necessary steps. So, the idea of this discussion is to give a flavor of the issues involved than getting into all the details of various steps involved in developing integration schemes. So, let us consider the problem of numerical simulation of the system governed by this SDE. Dx is a dt plus b dbt, initial condition at t naught is x naught. Now, I am now going to consider vector SDEs. So, x of t is d cross 1, db of t is m cross 1, a is d into 1, b is d into m. What we do is we discretize the time interval 0 to capital T into capital N intervals. We will assume that these time instants are spaced uniformly at a time step of delta which is capital T by n, and I will use the notation yk of n to denote the kth component in vector x evaluated at time Tn. Now, using Ito-Taylor's expansion and truncating at a suitable level, we can develop different numerical integration scheme, and one of the integration scheme is so called 1.5 order strong Taylor scheme, has this prescription. This can be derived by applying the Ito-Taylor's expansion. What we need to notice here is that on the right hand side there are now some random variables. This is a delta w is a random variable. This originates from multiple stochastic integrals. There is delta w here and there is a delta z here, and on the right hand side we are getting delta w whole square and so on and so forth. It would mean that these random variables are non-Gaussian, but this delta w itself are obtained as transformations are Gaussian. Delta w and delta z, they are obtained as transformations on two standard normal random variables u1 u2, that is 0 mean and unit covariance matrix. Let me emphasize again, the details of this formulary here can be worked out by application of Ito-Taylor's expansion, and the objective of this discussion is not to demonstrate the veracity of these derivations, but to illustrate how it can be used and to point out the intricacies involved in developing these schemes. Now, I will now consider a sequence of examples. So, let us begin by a single degree of freedom linear time invariant system under random excitation f of t, and let us assume that f of t, mean of f of t is 0 and autocovariance is sigma square delta of t1 minus t2. That would mean f of t is a 0 mean stationary Gaussian white noise process. Now, this second order differential equation can be recast as a set of first order differential equations, and they can be interpreted as stochastic differential equations, and the df of t, f of t is a white noise, we need to write it as increment of a Brownian motion process, and based on this representation and by using this integration scheme, we can get now a discrete map. Y1 is y1 of k plus 1 is x of t evaluated at t is equal to tk plus 1. So, similarly, this is velocity, this is displacement, and we get these maps, and we can begin with k equal to 0 and recursively evaluate these quantities and obtain the evolution of displacement and velocity as a function of time. I leave the exercise of verifying the details of these steps as an exercise for you, but I will show some numerical simulations. You can easily write a simple computer program to implement this. You need to generate these random numbers delta w and delta z starting from the u1 u2 that we need to generate here. This can be done using the methods that I already described, and we can use this transformation and generate delta w by delta z and plug it here. We can run these maps and we can get time histories of displacement and velocity. So, what I have tried to do is I have generated an ensemble of 5000 samples of x of t and x dot of t and carried out an ensemble averaging to say to estimate standard deviation of the response. System is linear and it is driven by a Gaussian white noise, and we know the exact solution for this case, and that exact solution in steady state I have shown only the steady state solution. The red line here is the exact solution. The blue line here is the estimate of the standard deviation for time varying from 0 to 40, and as you will see, as we reach steady state, the estimate from simulations matches quite well with the exactly known solution. This is the result for velocity process. Again, there is an acceptable match between simulations and the exact solutions. This is the result on probability distribution of velocity process, and this is represented by removing the mean and normalizing with respect to standard deviation, and we have shown here two graphs. The red one is the exact solution and blue is the simulations using this approach, and you can see that the mutual agreement is perfect. I have also shown some results here for extreme value distribution of displacement process in the steady state, and the extreme value is computed with respect to a time duration of 35 seconds, and on the x axis here the states of extreme value xm, which is the random variable, is normalized with respect to the steady state standard deviation of the displacement process, and on the y axis we show the probability. There are various results shown here. The full black is the simulation using 5000 samples. The dotted line is the a Gumbel model fitted to the extremes, and this exact is an analytical solution. It is not a really exact, but it is an analytical solution, and if the analytical solution based on level crossing statistics and first passage times is simplified to get a Gumbel model, we get this fourth line, and all of them are shown here, and you could see that there is considerable difference between the behavior of these four results. Now, let us move on to some nonlinear oscillators. As I already said in the beginning, as the systems becomes more complex, the Monte Carlo simulation methods play a crucial role in solving those problems. So, suppose let us consider now a nonlinear single degree freedom oscillator where there is nonlinearity in energy dissipation as well as in stiffness. This oscillator is known as Duffing van der Pol oscillator. If alpha equal to 0, we get the classical van der Pol oscillator with alpha and eta 0, and with epsilon 0, we get the classical Duffing's oscillator. So, again I assume f of t to be a white noise, 0 mean Gaussian, and I recast this in the state space form and interpret this as the Brownian motion, the stochastic differential equation, and in the we can now convert this SD into the map using the scheme that I have already provided, and in that I will need these quantities, and by applying that formula with these quantities we will get the map that we should use for simulating samples of this system. Now, if I take now epsilon to be 0, I have the system x double dot plus 2 eta omega x dot plus omega square x plus alpha x cube is f of t. So, this is a Duffing oscillator under stationary white noise excitation, and during our discussion on Markov vector approach to solve nonlinear oscillator problems, I have shown that for this system an exact steady state solution can be obtained for the probability density function of displacement and velocity. That is, the vector x dot is a Markov vector, and for the transition probability density function we can derive the governing Fokker-Planck equation, and in that if we consider only the steady state, that means dou f by dou t is put to dou p by dou t is put to 0, we can solve that equation and we get the exact probability density function, from which we can of course compute the exact variance of response, displacement and velocity. Now again, this is what I wanted to show here. This is a displacement response for a Duffing oscillator, and you see here there is a red line and a blue line. Red line is the exact solution using Markov vector approach, and the blue line is a simulation. So, you can see that the simulations with 5000 samples, the estimate matches very well with the exactly known steady state solution. Similarly, this is a solutions for velocity process. Again, there is a very good agreement between exactly known solution and the simulated response. This is the comparison of simulations on probability distribution function of the displacement in the steady state, blue line. The red line is a standard normal random variable. The displacement probability distribution is plotted on from the displacement process we have removed the mean and divided that quantity by the standard deviation, and that is, in that sense it is normalized, and when we the difference between the red and the blue line shows the influence of nonlinearity for this problem. It is not that these two lines are expected to match, they are known to differ. But velocity process, as we have seen in steady state, is a Gaussian random variable. So, here we should expect a perfect match between simulation and standard normal random variable, and that is what indeed we see for this example. This is results on extreme values, simulation, an analytical solution based on level crossing statistics, and from the simulated extreme values we have fitted a Gumbel model, and we show the probability distribution for these three situations. The simulation is also approximate given the finite number of samples that we use. So, all three solutions are approximate in nature, and this is how they compare with each other. This is a phase plane plot for the case of a Van der Pol oscillator. That means, I will now put alpha equal to 0 and I have taken epsilon as 0.1, and see Van der Pol oscillator has a limit cycle and there is no excitation, and you can see that here this trajectory is initiated somewhere here and it moves towards this the reminiscence of the limit cycle in the deterministic case, and because of the noise that we have applied, the trajectories hover around the stable limit cycle, and this produces a highly non-Gaussian response. And you can see here that when we compare the probability distribution function of the displacement in steady state with the standard normal variable, we see that there is significant departure, and in fact, if we plot the probability density function, the probability density function will be bimodal and it will appear like this, and in the probability distribution function it will appear as this kind of a wavy blue line that we are seeing here. This is that was on displacement, this is on velocity, the same features are observed here also. Again, results on extreme values, comparing with simulation. There are no exact analytical solutions here for response process, because the van der Pol oscillator under white noise does not belong to the class of problems for which there is an exact steady state solution available. So, we have to compare, there is no basis for comparing in this case. So, here we are showing the simulation, black full line is the probability distribution function of the extreme response on the 5000 samples that we obtained, and this Gumbel estimated is we assume hypothesize that the extreme value distribution is Gumbel, and we estimate the parameters of Gumbel distribution using the samples. Now, we can give a few more examples. One more example is single degree of freedom system with a tangent stiffness. So, this system, if displacement cross certain limits, the stiffness becomes very large and it offers infinite stiffness if displacement approach these values. That is what this tangent stiffness means. This system is now driven by Gaussian white noise as described here. So, we convert it into SDE, represent it as SDE and apply the integration scheme, and we again simulate. This problem is again belongs to the class of problems for which an exact steady state solution can be derived using a Markov vector approach. So, that is why this is specifically chosen as an illustration here, and these are the numerical values and certain notation that we are using in developing the solution. There is a parameter n which basically describes this distance. If displacement cross this, it encounters enormously high stiffness. So, for small value of n, the distance is very large, very small. For n equal to 5, the distance is very large. So, the response is almost Gaussian. This is the exact solution. As n becomes smaller, the response is now bounded between -1 and +1, and still smaller, it is almost highly non-Gaussian. These are exact solutions. Now, let us see what happens to simulations. This is a trajectory of simulated sample velocity versus displacement for large n. So, it is almost diffuses throughout the field. Now, n equal to 2, it is now constrained between these two places, and it in the velocity direction, of course, there is no problem. It takes larger range of values, and n equal to 1, it is now severely constrained. So, you can see that the such response of such systems is highly non-Gaussian. Now, again, since the steady state solution is exactly obtainable, we can now compare the estimate from simulations with the exact solutions. Exact solution is red line, blue line is a simulation. This is response displacement standard deviation versus time history. The similar time history for velocity response, again the match between simulation and theory is acceptable. So, we can continue with this. We can consider, for example, now a more complicated system, a 2 degree freedom system with cubic nonlinearities, and each of these system is driven by white noise. We can switch off one of them or keep both of them on. So, we have now the tools to treat this problem. We convert them into a 4×1 set of stochastic differential equations, discretize them, and we can run the map and obtain sample trajectories. So, this is phase plane, this is x2 dot versus x1 of t, this is x4 dot, x4 versus x3, that means the phase plane plot for the first coordinate and the second coordinate. In this example, we are assuming that the second coordinate is not driven, therefore, this trajectory is fairly smooth than the driven coordinate. This is quite rugged, this is fairly smooth. So, this is a result on extreme value response of the displacement process for the first degree of freedom. We could again of course plot the time histories of evolution of standard deviations, compute covariance, you can estimate power spectral density, you could do anything, but I am showing only limited results. The full line is simulation and dotted line is a Gumbel model for the simulated data. So, what we will do is we will close the lecture at this stage. So, what we have done today is that we have developed an integration scheme to handle certain types of stochastic differential equations. So, in the next lecture I will present a few more examples and then we will consider a few questions on how to estimate power spectral density functions and certain other response quantities. So, we will conclude the lecture at this stage.